because Carmen is not only one of my best collaborators, but maybe is one of my best friends. So it's really a pleasure for me to introduce her. Let me say a few things about her scientific activity. Carmen is full professor at the Instituto Astrofísico de Canarias and the University of La Laguna in Tenerife, Spain. She has spent a PhD fellowship at the University of Yale and at the Observatory of Carnegie, United States, and she has been also visiting scientist at the University of Padua. She is one of the major experts in the world concerning the study of resolved stellar population in the local group, and she has provided fundamental contribution in the study of the star formation history in local group dwarf. Just to mention, she's been the leader, the PI of the SEED project that has been awarded by a large number of HCT orbits in order to study in a very detailed way the star formation history of a significant large sample of dwarf galaxies in the local group. Nowadays, since a few years, she's exploiting also the Gaia data, trying to obtain very accurate investigation about the star formation history of the local disk. So please, Carmen.
Okay, thank you, Sandy, for the nice introduction and for the possibility to present these results here, which we share. I mean, these are common results. In fact, in the first view graph, I wanted to, to present you with the pictures, the main people that is involved in the new results that I'm going to present in this talk. They are a very nice team of enthusiastic people and good friends, all of them, I would say, which also provide each one of them a very specific expertise that is fundamental to the project. Okay, and so let's see, how do I? Okay, and so this talk is about the Milky Way. Okay, the Milky Way is this beautiful galaxy that we can see from a dark sky and where we live, and is the galaxy that we can study in more depth in order to decipher its formation and evolution in very great detail. And this is because we can characterize its stellar content and also the interstellar medium on a star-by-star basis, and use low-mass stars as proofs of the early universe and the whole evolution of the galaxy. The theory of galaxy formation and evolution, the simulations of galaxy formation and evolution are able now to provide very nice predictions and to reproduce the properties of galaxies in a very wide way and predict how they should form and evolve. But these models still have a lot of uncertainties in terms of which are the right parameters that actually govern galaxy evolution. And is therefore, by comparison with what we can observe in galaxies, that we could predict, we could help constrain the physical mechanisms that govern galaxy formation and evolution. So I was saying that, okay, to study the Milky Way, we use what we usually call galactic archaeology or near-field cosmology. And this is because we use, as archaeologists, we use fossils for that. And our fossils are stars, basically, okay? And in particular, low-mass stars are very important proofs of the early universe. And this is because the stars which are around 1 solar mass or a bit less live as long as the universe. And therefore, we can observe today the low-mass stars that have formed in the first star formation events in the universe. Therefore, their presence or not in a given stellar system is telling us when it began forming stars. Their properties allow us to characterize the first star formation events in terms, for example, of the amount of metals, of chemistry, of kinematics, and together with the stars in a range of masses that have formed later, inform us about the rate of star formation as a function of time and how metals, chemical enrichment has proceeded across the successive stellar generations. And we can characterize these stars through photometry, spectroscopy, astroseismology, etc. Now, in this talk, I'm going to talk a lot about the star formation history. So I wanted to tell what in this particular talk this means. And for that, I like very much what Paul Hodge proposed in the late 90s about what could star formation history be represented. And he proposed what he called the population box, which is a cube, basically, in which one of the axes is time, the other axis is metallicity, and the vertical axis would be the amount of mass transformed into stars as a function of age and metallicity. Okay, so this will be the definition of star formation history that I'm going to use in this talk. And actually, deriving the star formation history of the Milky Way was one of the primary scientific goals of the Gaia mission, as it was stated in the Gaia Red Book, which was the book where the main objectives of the mission and the mission design was summarized. To this end, Gaia is obtaining parallaxes, proper motions, luminosities, and colors for basically all Milky Way stars down to magnitude G of 20, which is approximately 10 to the 9 stars, or 1% of the stellar mass in the galaxy, or 1% of the stars in the galaxy. Gaia is also obtaining spectroscopy in terms of radial velocities down to magnitude G of 16, so somewhat brighter magnitude, and also chemical abundances down to G of 12, so even brighter magnitude. So because of this lower spectroscopic performance of Gaia, very quickly when Gaia was approved and was, started to be constructed, a large amount of ground-based spectroscopic surveys were planned to be complementary to Gaia, to provide the spectroscopy that Gaia wouldn't be able to provide. This means to observe spectroscopically stars down to a fainter magnitude limit, more stars, and also to a higher resolution to be able to obtain spectroscopic metallicities and abundances and radial velocity to a higher precision. So basically, every important astronomical society in the world, the Australians, the Chinese, the Americans, Europe, everyone has its own spectroscopic survey. Okay, and and this is a Gaia image of the Milky Way made by projecting in a particular way the luminosity of each individual star, while in the inset above would be an artistic view of the Milky Way. On this image of Gaia, I superimposed very schematically what are the components of the Milky Way. The Milky Way has, as any spiral galaxy, a very tenuous and low density and old halo that has about 1% of the mass of the galaxy, a central bulge, which is also quite old and which hosts in our case, we know now that it hosts the nuclear black hole. And then it has the most prominent feature in these galaxies like the Milky Way are the disk. Which in the Milky Way and in many galaxies can be divided in a thin and thick disk that we will see later what they are. Okay. In this talk, I'm going to basically discuss the properties and the star formation history of the halo and of the thin and the thick disk. Okay. Now, before going to discussing any, the results, our own results, that will be the second part of the talk, I'm going to make an introduction to show what is basically the state of the art in the field in exploiting this wealth of data that Gaia and the ground-based spectroscopic surveys are providing. And the first thing that I'm going to discuss is the chemical structure of the Milky Way disk. I have to say that I have just sampled some of the results in the literature. There are many other papers dealing with the same subjects, and I'm just picked one that I thought displayed the results in a more nice way to show in a talk. Okay, so these are results from Apogee regarding the chemical composition of stars in the Milky Way disk across a large range of galactocentric radius from the close to the galactic center to the outer disk, and also as a function of height above the plane. I'm going to I'm going to first discuss what this plot shows. Okay, this plot, what shows is well, this is a very widely used plot in galactic archaeology, which is the alpha over iron plot as a function of iron. Okay, on the y-axis, what we plot is the ratio of alpha elements as a function of iron, while in the x-axis we plot the amount, the amount of iron, basically. Ratio hydrogen. Alpha elements are, for example, oxygen, magnesium, sulfur, or silicon, and these are elements that are basically produced in very massive stars, which explode very quickly after they form as a type 2 supernova, right? So they are released into the interstellar medium very quickly after a burst of star formation occurs in a galaxy. On the contrary, iron is produced mainly in long-lived less massive stars that explode as supernova 1A. So okay, 1 second. Okay, so in a plot like this, when a given at the beginning of the life of the galaxy, or a given star forming burst occurs in a galaxy, at the beginning you have a large amount of alpha elements, so a high alpha over iron ratio that keeps more or less stable until supernova of type 1 start to explode. Then there is a feature in this plot which is usually called a knee, which marks the a sequence in which the alpha over iron starts to decrease as iron keeps increasing. Okay, and in the Milky Way we see, you will see in the plots that we have basically two sequences: one more or less at this alpha over iron of the solar level, and another one at the increased alpha over iron, as we can see here. Okay, if we focus in the plots, alpha over iron plots that correspond to near the solar cylinder, we can see that close to the radius of the sun and close to the plane, most of the stars, we see the knee here, the one sequence and the other sequence here, we see that most of the stars have low alpha over iron, and as we go to higher heights above the plane, so we go up to higher distances from the plane, the sequence of high alpha starts to populate more and more. And the same is true when we go to the inner galaxy and also to high heights above the plane. And on the contrary, in the outer galaxy, basically the only sequence that is populated is the low alpha sequence. This is showing a very interesting structure, chemical structure in the Milky Way, that is indicating already that up in the high up in the plane, the stars tend to be older. They have formed early in a situation of low iron and high alpha enrichment. And while in the outer disk, they possibly are younger stars, okay? But there is no direct information on age in this plot, okay? Then the other set of results that I would like to discuss, which is also marks the state of the art in the field regarding the knowledge of the stellar halo of the Milky Way, is studying the substructure in the Milky Way halo. Both from simulation and from observations, we have indications that the stellar halo has formed early and by accretion of satellites, okay, for satellites galaxies. And for example, these streams of stars that come from these accretion events are still seen in the physical space in the Milky Way. For example, this would be a picture of the sky with several of the streams still visible. And this would be pictures of external galaxies where also stellar streams are possible to be seen. However, these accretions dissolve fast in physical space. So these features that we see here in physical space should mark accretions which have happened not very long ago. Okay, simulations show that the signatures in the physical space of accretions dissolve very quickly, but that they can be still traced in the space of velocity or in the space of energy angular momentum. Okay, these are simulations that show this. Another way to find signatures of accretion is through chemistry, because chemistry, in principle, the photospheric the chemistry of the stars is not altered along their life, and we can measure it from the photosphere. And so chemistry is another conserved component that can help to identify all accretion events. And I'm going to show a couple of examples of these. The so-called Helmi streams were among the first bona fide accreted substructures that were discovered in the halo via velocities. In these plots, they correspond to these larger points that stand up in this velocity, different velocity combinations. Okay, this is one example of substructure that has found from velocities at the end of the last century. And this is another example of a substructure that was found chemically. Okay, in this case, a number of stars that were assigned because of their kinematics as belonging to the stellar halo. Okay, in this figure here, their alpha elements and their iron were measured, and it was seen that they were forming two different sequences in the alpha where iron versus iron plot. Okay, one sequence had higher alphas that were quite similar to the ones that were seen in the thick disk of the Milky Way, while another set of stars formed a sequence of lower alpha. This was interpreted as that the sequence of higher alpha was similar to the thick disk, could be a population formed in situ in the Milky Way, similar to the thick disk, while the low alpha would be an accreted population. This happened, you see, this is pre-Gaia and pre-massive spectroscopic surveys, okay? After Gaia and after this very massive spectroscopic survey, this has become really, really an industry. And there are many, 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 many works dealing with this, trying to find substructure mainly this is done in the plane of energy angular momentum. And substructures are found in this plane that are associated to potentially to different accretion events. This is one example, this paper, Naidu et al. 2020, in which they find these structures in a volume of 50 kiloparsecs from the galactic center. And this is a study closer to the sun, within 2.5 kiloparsecs of the sun. They find similar structures, and they also support the findings with by characterizing the chemistry of each one of these features, and seeing that they have actually a consistent chemistry. Okay. Of these results, I would like you to pay attention to this, because to the GES merger, this is Gaia, the acronym for Gaia Enceladus Sausage merger, because I will discuss this in more detail later on in the talk. Okay. Now, you see that this is really beautiful. I mean, we are starting to understand that the halo of the Milky Way has formed by accretion of substructures that we can actually identify. We see that there is a great amount of chemical structure in the Milky Way disk, etc. But the current, but you see that in all these, I haven't not really mentioned the word age, and age is very important. To be able to put order, to tell the story of the Milky Way, because the story has the time associated to it, and the current greatest challenge for substantial step forward in an understanding of the Milky Way evolution is, in fact, the difficulty to determine precise stellar ages for unbiased large sample of stars. It just cannot just be measured. We can measure velocities, we can measure chemistry, but we cannot measure ages, right? And they are essential, as I said, to establish a sequence of events and to correctly interpret what we measure in the context of galactic evolution models. And this idea has been highlighted very nicely by Milio et al. In 2017 in a paper called Plato as It Is, a legacy mission for galactic archaeology, where they explain very nicely how many, all the questions that could be answered about Milky Way evolution if we could infer ages to a precision of 10%. Okay, and yes, the kinds of questions that could be answered would be something like that. For example, what was the epoch of this formation? For example, was the thick disk in place when the big Gaia Enceladus sausage merger occurred, or was the result of this collision? We will see more about this later. What are the age and metallicity distribution across the disks of the Milky Way? Are they actually different, the thin disk and the thick disk, in terms of ages? They are really differentiated, or there is a continuum of properties. Also, we could answer whether accretion events induce star formation in the disk, and basically what is inducing star formation events in the disk. What could be the effect of radial migration, or whether there is a thick and a thin thick disk halo transition. Okay, these are kinds of questions that could be answered if we had ages. Okay, so our approach to derive ages is through Gaia color magnitude diagram fitting. Okay, as most of you know, I'm sure, because you know a lot about stellar evolution there. In the color magnitude diagram, okay, here I plot a color magnitude diagram computed with the Basti models and with a constant star formation rate for a given metallicity near solar. And you can see that across the main sequence, there is a very nice sequence of age that can provide, therefore, information about the ages in a given stellar population. There is also some dependency on metallicity, on the positions of the stars in the color magnitude diagram, but this is less important, especially in the main sequence. Therefore, if we have a color magnitude diagrams reaching to the all main sequence turn off, we have an excellent tool to derive the star formation history of a galaxy. And this, I'm going to explain how we do it in a nutshell. If someone is interested in more details, I can explain that after the talk. But here I'm going to explain just very quickly how we do it. Basically, what we do is we compare the distribution of the stars across the observed color magnitude diagram, with that in a set of model color magnitude diagrams computed with different star formation histories. And the comparison providing the best fit is giving us which is the star formation history of the galaxy. Okay, and as a star formation history, as I say, this is what we want. Basically, we want age and metallicity distribution, or amount of mass transformed into stars as a function of time and metallicity. Obtaining star formation histories from color magnitude diagram fitting is a very standard technique that has been applied to study the evolution of local group galaxies for over 20 or even 25 or 30 years. And so why has this not been applied before to the Milky Way? Well, it has been applied in very specific instances, but very rarely. And the reason is that we need to do this comparison in the absolute plane, okay? And to transform an observed CMD to the absolute plane, we need the distance of the stars. In a dwarf galaxy, we can use any distance indicator, variable stars, the tip of the red giant branch, whatever, to determine one single distance that allows us to transform the whole observed CMD into the absolute plane. In the Milky Way, this is not the case. In the Milky Way, we need the distance for each single star, and this is what Gaia has provided, and what is allowing to do this work in a very, in a very massive and comprehensive way for the first time. So the results of the CMD fitting, this population box or this star formation history, we can show it in many different ways. Okay, for example, we can plot it. Okay, the most complete plot would be this one. The age, a plot with betalicity as a function of age, with a given color scale indicating the number of stars. Okay. This is what provides the most information. Then if we collapse this plot for all metallicities, we can find the star formation rate as a function of age, like here is shown. Then if we collapse all the ages, we could provide the metallicity distribution function. Or the simplest and more synthetic way to express the evolution of a galaxy would be the cumulative star formation rate, which would be the fraction of stars that have been formed as a function of time, okay, with a fraction of 100% at the present time, okay? Okay, in all these plots, I'm going to show all at the left and yeah, at the right, okay? Now, we have tested what is our ability to recover the details in the star formation history with CMD fitting. And to do that, we have done what we believe is a very realistic test. And we have made a composite color magnitude diagram with 4 open clusters of a range of ages, which is shown here. These open clusters have been observed by Gaia, the same Gaia data release that we are using for the work. And we have derived the star formation history of this color magnitude diagram exactly in the same way as we do for the field galaxies. And by measuring the dispersion of age and metallicity with which we derive the age and the metallicity of each of the clusters, we have been able to show that we can derive age and metallicity to a precision of 10% or better, at least up to 6 gigayears, which is the age of the older cluster that we have checked. Okay, with tests with mock synthetic populations, we have been able to see that this is true also for all populations. Okay, now I have to say that this is not the most common approach to the age problem in galactic archaeology. Okay, the most common approach is basically trying to derive ages for individual stars through isochron fitting, okay? Through sophisticated ways of isochron fitting, okay? In this case, in addition, note that for our work, basically we need photometry, colors and magnitudes, and the parallax of the stars to have their distance, right? In this other more common approach, in addition to this information, we also need chemistry and hopefully astroseismic information to be able to constrain more the position of the star in the color magnitude diagram and be able to derive individual ages. Okay, and the last year in 2022, a number of papers were actually published with this approach, which were actually very, very relevant, and which were showing age metallicity. Let's see. Age metallicity relations for the Milky Way, for particular volumes of the Milky Way overall star formation histories. On the left-hand side, I have shown the fact that we also, this is similar, let's say, in concept to the age metallicity plots that we also produce. In our case, though, we are able to produce age metallicity plots spatially resolved for the Milky Way, as we will see. Now, there is pros and cons of both approaches, okay? In our case, since we only require photometry and parallaxes from Gaia, we have very complete samples, and therefore we can provide very unbiased age distributions for millions of stars in all evolutionary phases. Okay, we have seen that the precision in the age distribution is about 10%, and we need color magnitude diagrams reaching the oldest mean sequence turn-off. Okay, but this can be achievable with Gaia DR3 around 3 kiloparsecs from the sun, and with Gaia DR4 we expect to be able to go farther away. The fact that the selection functions are very simple allows this to obtain this unbiased star formation rate as a function of time and metallicity. However, the downside of this approach is that we don't have ages for individual stars. And this is a problem. This is a problem because we are not able to link ages directly ages with chemistry or kinematics of particular stars. Okay. In the other approach, the amount of information that is required is huge. Is huge in the sense that it's very costly to determine chemistry in astroseismology, for example, for the stars, and therefore. In general, this information can be obtained only for stars in particular evolutionary phases. The age precision can be of around 25% in general, and with very exquisite astroseismic information could be maybe 10%. The selection functions are very complicated, and this makes it difficult to obtain unbiased age distributions. But the good side of this approach is that ages can be obtained within some error for individual stars, which allows us to link directly ages with chemistry and kinematics, which is very useful to then interpret the results. Okay. In my opinion, these are very complementary and alternative approaches to a very difficult problem. And this is very important because the problem is difficult, so it's important to have multiple answers to important questions. Okay, so now I'm going to start discussing the results that we have obtained in this project so far. And I'm going to first show a couple of papers, results of a couple of papers that we published in Nature Astronomy based on data from Gaia DR2. The first one deals about the age of the stars in the Milky Way halo, and about this merger that I mentioned earlier on, the merger of Gaia Enceladus with the Milky Way progenitor, when this occurred, and what was the consequences of this merger for the Milky Way. Okay, this is what I discussed before. You remember that spectroscopically from the abundances, two populations were found in the Milky Way halo, which were interpreted as a signature of an important accretion in the Milky Way halo that happened at some point in the past of the Milky Way. In Gaia DR2, one of the spectacular results that really was very, very exciting to me when I saw this diagram, I was really, really excited, because seeing a diagram with a double sequence like this was something that was probably not seen before. And it was very quickly associated to these two populations, right? It was thought to be the confirmation that this accretion event in the Milky Way halo happened, and it was actually a very massive event, right? In this case, the blue sequence in the diagram, okay, the one in the left, some of the stars here had a spectroscopy, and it was seen that they were low alpha, and then therefore they could be associated to the accreted population. Sorry that here, unfortunately, the colors are opposite. These are the original colors in the paper, okay? And here the accreted population is shown in red, while in this color magnitude diagram, the accreted population would correspond to the blue sequence, okay? So this blue sequence would correspond to the Gaia Enceladus sausage, the accreted population. While the red sequence, the one to the right in the color magnitude diagram, because of the chemical composition of the few stars that had chemistry in them, was a composition like the thick disk, but had halokinematics, okay? At the time when this happened, I went to a conference on this subject, and there I could in situ realize the extent of the mess regarding what people believed about the ages of these two sequences, because some people, some groups were attributing younger ages to the blue sequence, some were attributing younger ages to the red sequence, and the lack of accurate ages for this in this CMD was really the main issue that was discussed, and that was preventing to actually interpret what had happened early on in the life of the galaxy. Okay, so what we did was to select the stars in the same color magnitude, that, select the stars with halokinematics. This is the CMD that we selected, which shows the two sequences clearly. And then to also select a color magnitude diagram of the thick disk as stars that were within a 2 kiloparsecs radio around the sun and above 1 kiloparsec from the plane. And these are the two CMDs that we analyzed. We derived the star formation history for both of them, and the age distributions as well, the age and metallicity distributions. And this is what we found. We found that the age distribution for the red sequence and the blue sequence was basically identical. Okay, within the errors, it was basically identical, and it was somewhat older than that of the thick disk. Okay. Considering under the reasonable assumption that when this galaxy Gaia Enceladus sausage was accreted to the Milky Way, it would stop forming stars. When this red and blue sequence start, when there is no more stars in this sequence, we can use this information to mark the approximate time of accretion of Gaia Enceladus, which would be, we concluded, would have been previous to 10 gig years ago, maybe 11 or 10 gig years ago. Okay, which is in agreement with other results that some people produced later. Then it's also very interesting that at the time where we concluded that the accretion of Gaia Enceladus should have taken place, we see that in the thick disk we found a very prominent burst of star formation in the thick disk, which could be caused by this accretion of Gaia Enceladus. Then the fact that the same age distribution, or very approximately the same age distribution, is seen in the blue and the red sequence could be interpreted as with the idea that the red sequence were stars that were already formed in the Milky Way disk when the accretion of Gaia Enceladus took place, and that they were scattered to halo orbits because of the strength of because of the energy of the merger. Okay. In this work, I would like to also, if we have the same age distribution, then what produces the double sequence? Obviously, what produces the double sequence is the different metallicity distribution. We could recover the metallicity distribution also for the three sequences. Here it is depicted by the blue, the red, and the black line. This is the lines show the metallicity distribution that we could recover from the CMD. I have to highlight that we don't use any metallicity information for the CMD fitting. Okay, so this is what we recover. And in the shaded histograms is shown the distributions of metallicity derived spectroscopically. You can see that they are not exactly for the same stars. You can see that the agreement is actually quite good. Okay, and also in the red panel, I would like to show. And in the upper part, you see the observed CMDs, and in the lower part, you see the solution CMDs. You can see that they are basically indistinguishable, and the merit of this is only that of the stellar evolution people in Teramo, who produce the models that are able to, to reproduce the data in such a nice way. Okay, the second work that I wanted to mention is this, which we call the recurrent impact of the Sagittarius dwarf on the star formation history of the Milky Way. In this case, what we did was to derive the star formation history, the overall star formation history, for a volume of radius 2 kiloparsecs around the sun. This is the corresponding color magnitude diagrams. Again, you can see the observed and the best model, and you see that the agreement is actually amazing. Again, merit of Santi, Adriano, and collaborators. And the star formation history of this volume, we actually produced several, and we averaged them together. And it is characterized by let's say one striking burst of star formation occurred around 6 years ago, between 6 and 4.5 years ago, and another two around 2 and 1 year ago. Okay. And well, we were very puzzled by this feature, these very prominent features in the star formation history. And then we started to look what could be the cause of this. And we saw that there was that these epochs of enhanced star formation in the Milky Way disk coincided with the inferred main pericentric passages of the Sagittarius dwarf galaxy that is currently in the process of being accreted by the Milky Way. In particular, it seems that the studies seem to date the first pericentric passage of Sagittarius to occur around 60 years ago. And well, these are different determinations, okay, by different authors, and you see that they all cluster around 6, around 2, around 1 year ago. So there is tantalizing indication that actually these features in star formation history of the Milky Way could be caused by the pericentric passages of the Sagittarius dwarf, which is also in agreement with the fact that when Gaia Enceladus was accreted, also a burst of star formation occurred in the Milky Way. Okay, and now I would like to spend, if I have 5 minutes more, to show work in progress. Do I have 5 minutes more?
Yes, Carmen, please.
Yeah. Okay. So currently we are analyzing a cylinder of 1 kiloparsec radius around the sun and height plus minus 3.5 kiloparsecs from the plane. Okay. And we are slicing this cylinder as a function of height above the plane. And we are fitting each one of the color magnitude diagrams. In this right panel, I show the different color magnitude diagrams that we are analyzing as a function of height above the plane. These are the ones closer to the plane. You see that they have a very nice blue sequence with a very extended to right magnitude, showing a lot of young stars. And this blue bright sequence starts to become fainter and less populated as we go in this direction to higher distances from the plane, okay? And when we go very high up in the plane, basically it has disappeared completely. I have to say that the kinematically selected allostars that were associated to Gaia Enceladus and the in-situ halo are removed from these CMDs. That's why the double sequence doesn't appear in any of them. And okay, from the previous work, we have done a complete update of the ingredients and methodology. Basically, we have using the new data of Gaia DR 3. We are using now the updated stellar evolutionary model set BASTI IAC, published in 2018 and later. We have also updated the color magnitude diagram fitting code to a more complex one. We have updated the Euro treatment. We have updated the extinction map. So that's why it's taking a bit long to actually publish these new results. Okay. So I will show a number of plots for each one of these slices in the Milky Way disk. I will show a number of plots. I will show the color magnitude diagram where the stars are as a function of distance from the, okay, this is distance from the sun, but basically in the radial direction, okay? In the x-axis is the radial direction, in the direction of the galactic center, and in the y-axis is shows the height below and above the plane. Okay. Then on the lower right panel, I will show the age metallicity plane with the mass transformed into stars color coded, being red, a large amount of mass. And then in the upper right panel, I will show the star formation rate as a function of time, basically. So collapsing these for all metallicities. And I remind, as I said before, that in the star formation, in these two plots, the sense is that old stars are, old ages are to the left and young ages are to the right. And that we, this picture here is to remind, to give the sense that we're actually covering the whole history of the galaxy from the very first stars to the present time. Okay, so what we are going to see is how the age-metallicity relation in the star formation history evolves across the Milky Way disk from from high distances to the plane of the galaxy, and we will see that there are very distinct star formation episodes that are not the same everywhere. Okay, so okay, I'm gonna pass this relatively quickly, so it will be seen as a kind of movie. First, I would like to ask you to focus on this plane, on the star formation rate as a function of time, okay? And you will see how the star population becomes progressively younger. The peak of star formation is younger as time goes on, as we go down to the plane, and how new bursts of star formation progressively appear with the stellar population becoming progressively younger as we go to the plane. This is the last snapshot corresponding to a distance of 50 parsecs from the plane, and you see that a burst of star formation seems to be occurring in the Milky Way disk right now. Okay, now I'm gonna pass this movie again. But now I would like you to focus on the age metallicity plane, okay? And you will see that the star formation rate as a function of time is not the whole story, that a lot is going on also in terms of metallicity. For example, in this first snapshot, we see that this first burst of star formation, which lasts between, let's say, 13 maybe and 10 years ago, has actually a rich metallicity structure from minus 0.5, which is more or less the metallicity of the thick disk, going to a higher metallicity. There is an age metallicity relation here. Okay, so anyway, this is the first snapshot, and then now please focus on this lower panel, and we see that as we go down to the plane, this burst, this star formation episode becomes more and more metal rich, and new features appear. For example, here we see this feature appearing at a higher metallicity at an age of around 10 gigayears, which could be this burst that we linked to the accretion of Gaia Enceladus, but this is a burst in the Milky Way disk. Then when we go, we see that, well, that this burst becomes even more prominent as we go down, and around 700 parsecs from the plane, a new feature appears here, okay, a new burst appears, which occurs at around 8 gigayears, and we believe could be linked to the accretion of the Helm streams, which some works date that may have occurred around 8 gigayears ago, okay? Then here, well, and also in some of the features above, you see that there is this other feature here, which is the same feature that we have seen in the previous study around 6 years ago. We have this burst of the star formation that we linked to the accretion of Sagittarius. In the age metallicity plane, we see that there is actually a gap of star formation occurring, okay, which will be very interesting to interpret, because many authors have claimed that that a break in the star formation could could mark the transition between the thick disk and the thin disk. The problem is that we find this at around 7 years ago, which seems to be a bit late, but we'll see. Could also be that star formation in the Milky Way had more or less stopped, and the accretion of Sagittarius has reignited it again. Or there is also some models, galaxy evolution models, the Obliga simulations, that show some examples of galaxies in which a temporary reduction of the disk size occurs due to a lower gas accretion, and then when gas accretion is resumed again, there is a reignition of star formation. So anyway, this will be a very interesting feature to interpret. And then anyway, you see that as we go down to the plane, closer and closer to the plane, there is a lot of structure going on at the young part of the age metallicity diagram. And that's about all I wanted to say. I can leave maybe this view graph, well, showing that I listed a number of questions at the beginning of the talk, and I think we have preliminary answers for them. For example, we wanted to know what is the epoch of this formation and whether the thick disk was in place when the merger with Gaia Enceladus occurred. And it seems that, yes, the disk was already formed, but when Gaia Enceladus merged, a burst happened. We can add information to the age information to the metallicity distributions across the disk. We see that the age metallicity relations are very rich in structure, and that there is a very nice transition between the thick disk and the thin disk that is actually a continuum of properties. We have seen that accretion events seem really to induce star formation in the disk, and yeah, and that's all I wanted to highlight. So I can take questions now if you like.
Okay, thank you, Carmen, for this very complete talk. I cannot say interesting because it would be a very biased interpretation from myself because I have involved in it. So please, if someone has any question to Carmen. Any question?
Santi, there's Enzo raised his hand.
Sorry. Please, Enzo. Sorry, I didn't see.
So first, thank you very much for the very interesting talk that you have given to us. This is, I can say, because I'm not involved in this, so I say that because it's very, very interesting. I have a couple of questions, let's say. Do you think that this is a very powerful method, no? This is clear. Do you think that with the present or with the next set of data from Gaia or from other survey, we can apply this in the Magellanic Clouds, for example? Or is it too far away? Or there are problems that you can see to apply this for reconstruct the story also for the Magellanic Clouds, which is interesting.
Yeah, in the case of the Magellanic Clouds or in the case of other dwarf galaxies, it's actually better to obtain specific observations for them. Note that Gaia is reaching to magnitude 20, basically, right? While from ground-based observations, we can easily reach, for example, magnitude 24. These 4 additional magnitudes that we can reach from the ground mean that this kind of data reaching the oldest main sequence turn-offs can be obtained from the ground for the Magellanic Clouds, for example, right? Then for more distant galaxies like satellites of Andromeda or the dwarf regulars in the local group, the kind of the necessary data can be obtained, and we have done that with the Hubble Space Telescope. We can reach the necessary depth. So what Gaia has really enabled has been to open this field to the Milky Way. It is a bit contradictory that the galaxy that is closer to us and the one that in principle we can study better is the one that we are studying last with this kind of technique. And it's because we needed the individual distances that Gaia is providing. But yeah, in the case of the Magellanic Clouds, Gaia is able to reach a few magnitudes in the red giant branch, and wouldn't be possible to do this with Gaia data. But at the same time, Gaia data, what can provide for these other galaxies, the Magellanic Clouds or the other satellites of the Milky Way, could be the possibility maybe to clean the color magnitude diagrams from foreground stars, for example. So, or provide even better distance or complementary information. Yeah. Thank you for the question.
Thank you. Thank you. Thank you.
Okay.
Can I ask something? Yeah, can I go something?
Yeah, sure.
So, Carmen, this was really, really brilliant talk. I liked it a lot. Thanks. I have a billion of questions, but I'll just ask one.
Okay.
So, what is the nightmare in this job? I mean, deriving from the CMD to star formation history, I guess that there are a lot of parameters, a lot of lots of assumptions on, and also both on the observations and on the modeling. What is the really nightmare that changes everything, or that has the strongest impact, at least?
Okay, let me see. What's the nightmare? I think, let's see. There is a number of parameters that you have to assume. For example, you have to assume to construct the synthetic CMDs. Well, first, the stellar evolution models. But we have seen that even comparing with other model sets, we have seen that the results doesn't change heavily, at least not the main conclusion. So this is not a big nightmare. And I think it's saying that the stellar evolution models really, really are in a stage revolution, fantastic. No? Then you have to assume binaries. Under reasonable assumptions for binaries, the results change a bit, but not dramatically. So I would say that this is not also a big deal. Then what else? Then in this process, we actually divide the synthetic CMD in what we call simple stellar populations, which are populations in small ranges of ages and metallicity. And we have noticed that the structure in the grains in this, the granularity in the star formation history depends a bit on the size of these simple stellar populations, whether they are very small or very large. So we have seen that if we want to recover, for example, with high precision the age of the open clusters, we need to have very small bins, but sometimes we have these very small bins, sometimes the solutions are very granular, and I'm not sure whether we can believe this granularity or not. So we are doing tons of tests to be sure what we can trust and what we cannot trust of this large amount of detail that we can see in the solutions, for example. What other nightmares? Well, I think these are the basic ones. Well, another nightmare close to the plane is reddening. I mean, you need a very good reddening map to be able to correct for reddening. This is much less of a problem when you are at layers at higher distances from the plane. Yeah, I think this is more or less the main things.
Thank you. Santi, I think there's also Michele Fabrica.
Please, Michele. Okay, please, Michele.
Hi,
yes,
Michele.
Ciao. Hi.
Hi, ciao.
Nice to see you again. I have just a curiosity or a suggestion to you. If you introduce also some constraint on metallicity, for example, from Gaia DPRP metallicity derived from DPRP or from LBS. the star formation rate should change. I'm very curious on this. If the granulation or the final output you obtain is changed by using also this constraint.
Mm-hmm. We're not doing this, because we are verifying that actually the metallicity distributions that we find are very much in agreement with the observed ones. Okay, without, I'm looking for this plot, sorry, this plot, for example. Okay. Yeah, I mean, we derive the metallicity, okay, of these without putting any of these constraints that you are suggesting in the metallicity, and we find almost exactly the metallicity observed. In the case of, for example, in one case that I haven't shown is that we have derived the star formation history of the Gaia nearby star catalog, so the 100 parsec bubble around the sun, and for that we have Gaia metallicities. Okay, so the distribution of metallicities has exactly the same peak as the measured one by Gaia, but ours is narrower. When we apply the errors, the measurement errors of the Gaia metallicities to our metallicity derivations for each star, we recover the same width. So we have not seen the need so far to do that. As long as we have these very deep color magnitude diagrams reaching the All-Main sequence turn-off. Maybe if we are in a more complicated situation with less deep diagrams and so on, then maybe we could consider this. But one has to take into account that actually the errors are relatively large, especially with LBS. And if you don't use LBS, but you use the ground-based spectroscopic surveys, then there you have selection functions that would be a problem as well, that would bias your metallicity distribution. So far when the observations are so good and the diagrams are so good, I think we wouldn't gain much. And I'm happier by then a posteriori comparing the metallicity distribution that we find with what is observed by the spectroscopic surveys, and this is a way to actually show that our results are reliable.
Okay, thank you. Thank you for your talk.
May I add a comment on the question from Michele? I would like to say that for sure we need to go to define the main sequence turn-off to determine the age. But luckily enough, the giants are a very powerful constraint on the metallicity. So this is the reason, I think, for which with this method we are retrieving extremely accurate metallicity distribution that well compare with the observational data, let me say.
Mm-hmm. Yeah. Okay. So
another question? I have just a curiosity, Carmen, because I know you have mentioned the data release from Gaia. No? So you say with this new release, we can observe with a larger accuracy stars that are far away. The point is, with the additional data that the new Gaia catalog will release concerning, I don't know, kinematical properties and so on, do you think that it will be possible to add additional piece of information to the whole puzzle that we are building concerning the galaxy?
Yes, yes. You see that what I have discussed so far and what we have been doing so far is we have selected the samples based on geometry only, right? Based on where the stars are, for example, in this case, as a function of height above the plane or as a function of radius, galactic radius, etc. When we have a lot of chemistry measurements, for example, a lot of stars with alpha information or a lot of stars with kinematics, then what we could do would be to select samples kinematically or chemically. For example, we could select thin and thin disk kinematically, or populations that are kinematically distinct. For example, even an accreted population that is being singled out from its kinematics, it could be selected, and then the star formation history be performed on that particular population. Or the alpha-rich and the alpha-poor population, do star formation histories separately for the two. I think this is the way for this method to overcome the drawback of not being able to associate ages to particular stars which have kinematics and chemistry, because we always have to work with the age distributions, but by selecting particular populations based on chemistry or on kinematics, then we can tackle the issue of the ages of particular populations that are characterized kinematically or chemically. So yeah, this is, Santi, thank you for this question, because this would be very much the next step forward in the project. Yeah.
Okay, thank you. Okay, other question? I don't think so. So we warmly thank Carmen again for this interesting talk that I think has been also very instructive also for persons that are not really fully involved in this kind of investigation. And I warmly thank them for attending this meeting, this talk. Okay, so thank you, Carmen, again.
Okay, thank you to you for the interest and for having me. Okay, ciao, ciao.
Thanks. Thanks, Carmen.
Thank you.
Thank you.
Bye-bye.
Thank you.
Bye.
Thank you, Carmen.
Bye.
Thank you. Bye.
Very interesting.
Bye-bye.
Bye.
Bye.